It's no secret that one of the most challenging aspects of deploying Asterisk and other voice applications on Kubernetes is the networking. It's a clash of design. Kubernetes was designed with web apps in mind, but most VoIP systems need much more powerful network features. In this talk, we will discuss the networking solutions which are available inside Kubernetes for both bare metal and cloud systems. We can do VoIP on Kubernetes today without breaking its intent and without compromising other applications. But first, why run Kubernetes with VoIP? There are a number of potential reasons you might want to run your applications in Kubernetes generally. Process control, automation, API tooling, CI/CD, product support, great patterns for web apps, container-based patterns. The list goes on, but let me highlight a couple which are of particular interest to VoIP users. Image-based deployments. Managing applications deployed to legacy general-purpose OSs is a constant battle of permutations. Does the OS have version X of Y library installed? Is application X+1 still compatible with library Z-2? Does distribution A include a recent enough version of library Y? If app C needs library Z-2, but app D needs library Z+1, how do I reconcile these two? Voice applications in particular have a long history of these types of problems. Asterisk, FreeSwitch, Camelio, etc. They're all very complex, large systems with many external dependencies. Running combinations of these things makes maintenance of such systems an enormous problem, which is often solved by simply locking down entire systems for years, leaving the systems vulnerable to a relentless march of security flaws, missed performance improvements, and lock-in to legacy hardware, which becomes more expensive to maintain and difficult to find over time. The idea that you can reliably build and distribute identical images with all dependencies included within and use them anywhere is an enormous benefit to scalability, reliability, and reduction in overhead. These self-contained images can be run through a large battery of internal and integration tests. And when they're run inside a Kubernetes environment, they're gifted with a large number of operational parameters which are able to be held constant across data centers, infrastructure providers, hardware, etc. In short, you can build and test once and then immediately deploy anywhere. The promise of image-based deployments is that this whole class of problems and operation-related headaches just disappears. Separation of concerns. Related to this is the idea of separation of concerns. Discretely managing general-purpose computers with big, bloated operating systems should be a thing of the past for high-volume servers. Indeed, with Kubernetes, we have new operating systems like Talos, CoreOS, Flatcar, and others, which eliminate much of the management of the operating system, leaving the administrator instead to focus on the cluster level, Kubernetes and applications running within it. This abstraction of the OS from the application operating environment is one aspect of the separation of concerns afforded by Kubernetes. Following from that, individual nodes or machines inside that cluster, in the ideal case, no longer matter either. With software-defined networking, even addressing and routing is handled automatically and dynamically. Even at the application layer, this concept is in play. Because deploying an application is both easy and generally side effect free, it is easy to run many sets of applications, splitting out the roles so that each performs a more limited task which can be made more thoroughly tested and which deployment can be independently scaled, leading to a greater reliability and greater efficiency. In many legacy VoIP deployments, the overhead involved in running even a single instance of anything means that there is a great motivation to put as many functions as possible into that one application so as to reduce the number of moving pieces and complexity of the system overall. Kubernetes turns this motivation completely upside down. 3 flows of VoIP. Kubernetes offers a lot of benefits, but there are also problems. In particular, the special networking needs of VoIP are often misaligned with the facilities of Kubernetes. VoIP systems are composed of 3 main network flows: SIP, RTP, and WebRTC. SIP is the core of most VoIP systems. It's stateful, but usually transported across the connectionless UDP protocol. Kubernetes, on the other hand, was built around HTTP, which is ideally stateless, but is usually transported across the connection-oriented TCP protocol. Here we see the first mismatch. HTTP requests are generally atomic. There is a request followed by a response, and that's it. There are a number of technologies, such as cookies, sessions, JSON Web Tokens, which allow for continuity across multiple requests, but critically, they have been engineered to not be reliant on intermediate layers, such as load balancers and proxies, to be aware of that session. Even then, when longer-lived communication sequences do exist, you can rely on the connections established by TCP to make sure that subsequent packets are sent to the right place. SIP flows, on the other hand, are entirely about sessions. It's in the name, Session Initiation Protocol. Yet VoIP systems generally are unable to be as flexibly separated, scalable, and payload ignorant. We have to track IPs and ports, intermediate hops, and even logical calls within sessions, all for the most part anyway, with protocol-aware entities at every point across durations which long outlive connection associations for the transports involved. Worse, the typical load balancing algorithms used by HTTP load balancers, such as source IP and IP source pairs, are not very helpful when you're dealing with large trunks carrying hundreds of calls between the same 2 proxies. Finally, SIP endpoints generally have to be aware of their parent IP addresses. NAT is manageable but antithetical. Kubernetes is built on NAT, and the separation of networking concerns and awareness thereof is a core design precept. If you thought SIP was bad, let's talk about the Real-Time Transport Protocol, RTP. While SIP at least involves a single, predictable port, and you can easily handle many thousands of calls through a single proxy, RTP is more problematic. RTP involves essentially random port allocation, typically involving huge swaths of port ranges. Kubernetes has no facility for even the concept of a range of ports, which means adding tens of thousands of ports to a service is both tedious and inefficient. RTP is bound closely with SIP because in order to establish an RTP link, you have to establish and negotiate both sides, knowing all the information about each. This is typically done through SDP, the Session Description Protocol, carried over SIP. Oops. That whole separation of concerns with Kubernetes architecture rears its head again. Lastly, while SIP is able to handle large numbers of calls per proxy, and hence per external IP, RTP is not so lucky. RTP involves constant real-time data flows. This makes connections easier to maintain, but it also makes demand for throughput at each layer much higher. While you may have a sufficiently scalable system with a single or redundant pair SIP proxy, it is unlikely that a single RTP proxy will be able to handle all of the calls by itself. The irony is that the most complex of the VoIP protocols is actually the easiest to get working inside Kubernetes. Because WebRTC is, well, web-based, it generally fits the patterns used by the web, which are patterns around which Kubernetes was built. With WebRTC, you also get inclusion of protocols and services such as ICE and Turn, which allow you to lose awareness of your external networking and greatly ease the operation of VoIP components behind NAT. SIP and all session negotiation is generally handled over HTTP or WebSockets, which works perfectly within Kubernetes. This isn't to say that WebRTC is all roses, though. Ultimately, it is just a mix of a number of different underlying protocols and services, most of which are also available with some effort and a healthy serving of compatibility constraints to classical VoIP traffic. As long as you are not having to directly handle media, WebRTC works pretty seamlessly. But once you need to pass media through your infrastructure, even if it's just for a few prompts, many of those same woes from RTP come flowing back into the mix. You need large numbers of ports, which have to be negotiated. You need to know your addresses. You need to be able to handle multiple proxies. So we have all of these difficulties, but we still want to use Kubernetes. What do? We can boil most of these problems into two main categories: addresses and ports. Both SIP and RTP services need to know the externally facing addresses, regardless of whether they are NATed, or in many cases, these addresses even need to be predictable or fixed. RTP needs a lot of ports, and Kubernetes services don't handle bulk ports all that well at all. So your first line of attack is to make liberal and effective use of proxies. While you can't generally make use of HTTP proxies or load balancers for VoIP, there do exist effective SIP and RTP proxies. For SIP, you have Kamailio and OpenSIPs. These SIP proxies can handle large numbers of concurrent calls and high call rates when configured appropriately. These proxies can do a whole lot more, and it is common to add all manner of additional logic to them. For the purposes of ingress into Kubernetes, though, we want the configurations to be as stripped down as possible. The less they do, the better. You can still use SIP proxies for additional layers, but separate those features out into the subsequent layers. A common design for this is to have an ingress layer, which may or may not include access control, and then set a more fully featured SIP router on the inside. The idea here is that you want your limited resource here to be the addresses, not the compute power. So we put the minimum number of ingress proxies necessary, usually 2 or 3, even for very large installations, with fixed external IP addresses, and then branch out to scalable sets of internal proxies on the inside, where you can use all the additional tools of Kubernetes to scale freely. So we have 3 or more layer deployment for the SIP infrastructure. 1, ingress proxies. 2, routing proxies. 3, media servers, such as Asterisk. Each node of layer 1 can handle a lot of traffic and need not scale much, if at all. Layers 2 and 3, on the other hand, can scale easily and even automatically without external intervention. For RTP proxies, you generally only need 2 layers: ingress proxies and media servers, since you don't generally need to perform many additional manipulations of RTP before hitting those media servers. Proxies let us reduce our address requirements. but we still have to address addressing. There are a few ways to do this. External IPs on internal pods. The CNI, Container Network Interface, defines the interface for controlling network configuration and operations in Kubernetes. A CNI controller is responsible for implementing the CNI to make the network work. However, we generally use the term CNI to mean the controller of the CNI, not just the interface itself. Most CNIs specifically avoid assigning publicly accessible IP addresses directly to pods. Unfortunately, Kubernetes was designed with NAT in mind, and NAT is used as a de facto security model. This is a shame, since it could easily have been designed much more simply just with IPv6. Regardless, non-NAT-based security models were an afterthought. And even now, not all CNIs support network policies, which are the more robust mechanism for network-level security. As a result, most CNIs will not allow you to assign pods external IP addresses. Most is not all, however. In particular, Nokia designed the DANM CNI, that's D-A-N-M, specifically for use in communications infrastructure. The beautiful thing about DANM is that you can use your default CNI for most services, Cilium, Flannel, what have you, in the cluster, and then assign public IPs directly to just your ingress proxy pods. In this way, you get the best of all worlds. Default secure pods in the cluster, specific pods to obtain directly allocated public IPs, and yet all pods get to communicate locally without NAT to each other. So DANM seems like the perfect answer. The problem? It won't work in all scenarios. In particular, DANM will not work on most cloud provider installations because it uses mechanisms such as IPVLAN, VXLAN, and SR-IOV to achieve its success. Calico is another CNI which supports, with some effort, directly allocated IP addresses, but it relies on BGP, which is also not generally supported by cloud providers. So for many installations, these special CNIs are not an option. One-to-one service-to-pod mappings. While you generally cannot reliably have generic load balancers work with SIP, you can use a load balancer as a crude proxy. If you create a load balancer for each ingress proxy, and you only assign a single proxy to each load balancer, you effectively disable load balancing since there is only one target. But you gain a crude proxy which will forward a SIP port for a public IP on the load balancer to the private cluster IP of the ingress proxy. This is generally a fairly wasteful mechanism, but it will work with most any cloud provider. Note that many cloud providers do not allow mixed TCP and UDP on the same load balancer, or even if they do, their Kubernetes interface for configuring the load balancer does not. So if you want to serve SIP on both TCP and UDP, you may need to double the number of required load balancers again. Then we have host networking. Host networking is Alexander the Great's Gordian knot solution. It bypasses Kubernetes networking entirely for your ingress proxies. This is definitely a brute force mechanism, but it isn't as bad as it may sound at first. Only your ingress proxies would run with host-based networking, and they would still be able to talk to the rest of your cluster directly, even though their own IPs will be outside the cluster's subnet range. This is because many functions of Kubernetes require the ability to communicate between the host, so that communication pathway already exists. The biggest downside of host networking is that the ingress proxy instances are then tied to a particular host because the fixed IPs themselves are also tied to hosts. There are a number of ways to handle migration of IP addresses between hosts, but they are generally infrastructure dependent. Cloud APIs, BGP, virtual IPs, etc. RTP addressing. So far, we've only talked about SIP addressing, but RTP has addressing concerns too. For the most part, the same solutions apply, but RTP is often a bit more flexible. Many times, the actual IP addresses of RTP servers do not need to be pre-registered. Access control is relegated to SIP, not RTP. In this case, there's no need to have fixed or predetermined IP addresses for RTP. You just need to know what IP you appear as and in the moment. This makes host networking much simpler and more attractive for RTP. Running RTP proxy or RTP engine as a daemon set on a number of nodes to guarantee one instance runs per node is a really easy option. Ports. As we mentioned earlier, SIP ports are pretty easy. We generally only have a handful, so defining them within Kubernetes constructs is natural. For RTP, we still have a problem. We basically cannot use their services at all for RTP. That leaves us with only two options: host networking and direct IP allocation. Let's talk a bit more about Kubernetes services. Kubernetes services are composed of a couple different things. The service itself is a load balancer, which offers a fixed IP address in the cluster or outside the cluster, over which traffic will be load balanced to a dynamic set of ultimate destinations or pods. To operate, though, Kubernetes also needs to track those destinations. Conveniently, those are exposed as endpoints. Every service which is created has a corresponding endpoints resource, which is automatically created. This resource is always kept up to date with the current set of pod IPs for each matching service endpoint. While we can't make use of the service directly for RTP, the endpoints of that service can be very useful for directly routing traffic to providers of that service. And while a service only offers a handful of ports for load balancing, you can address any port on the pod when communicating directly. Internal components. So we have the proxies figured out. But if we look at the internal components, don't we have all the same problems? Our proxies need to be able to communicate to our internal components, and those internal components are going to be a dynamic set of machines. We are going to need to communicate using both SIP and RTP. We are still going to have the problems if we try to use a load balancer which is not aware of SIP or RTP. This is where the service endpoints comes into play. We need a way to always know the IP addresses of a dynamic set of VoIP systems. We could try to query this periodically manually, but services do this already with those endpoints we discussed earlier. We can create a service which points to all asterisk servers, for instance. And even though we can't use that service directly as a load balancer, we can use that as a source of truth for discovering those asterisk servers discretely. Likewise, the asterisk servers can use a service to always know the full set of proxies. These data can inform SIP peering configurations and access lists. This is where the real power of Kubernetes comes into play. We are given an API which will allow us to keep up to date any time matching pods are changed, added, or removed. This happens almost instantly. All we have to do is translate that API into configuration for Camelio, etc. To facilitate this, I have written two important tools. Whether you use them directly or merely as a pattern, they reflect an important pattern which any Kubernetes administrator or system developer needs to internalize. They bind Kubernetes API calls to the real-time, runtime configuration of your program. My dispatchers tool updates and tells Camelio to reload whenever service endpoints that it monitors change. My *config tool does the same thing for *. When you move your VoIP application to Kubernetes, you want to resist the urge to bundle configuration statically with your container image, not just because it isn't secure, but because the dynamic configuration is the only way to use Kubernetes to its full value. To embrace Kubernetes, you must also embrace dynamism. All configurations should be derived from a canonical source, where that source is, ideally, an API itself. You should now have a general understanding of the networking difficulties and the available solutions when running VoIP applications inside Kubernetes. Issues like addressing and the awareness and management thereof, and limited resources that we have available particularly for external IPs, ports, and using large numbers of those ports. We have solutions like using good and flexible CNIs, Denim, Calico, whenever you can. You can use one-to-one service-to-pod load balancers, and host-based networking when all else fails. Services and endpoints. Even if you can't use a service directly, the endpoints of a service points to the pod IPs which you can use. We're VoIP people, and many of us have a lot of reasons to not run in the cloud. If you're looking to run Kubernetes on your own infrastructure, be sure to keep my employer in mind, Sidero Labs. We build a highly focused operating system and many management tools to run Kubernetes on your own infrastructure as easily or easier than those hosted on cloud platforms. Here's a list of all the resources we talked about today, an example deployment scenario, and some other useful links. Thanks for your time, and I hope you enjoyed this talk. Do we have any questions?